Dear listeners and viewers of this Science and Reason program, we are going to talk about modern science and the Catholic Church, which of course is a very delicate subject. We know that Galileo Galilei, about whom we are going to talk today, who had some problems with the interpretation of the Church about the movement of the heavens. On the other hand, real scientists really agree, even now, that Galileo couldn't prove the movement of the sun, which he defended in accordance with the system of Copernicus. Now, this is already about what we are going to talk about, but I want to just have a little introduction about this thing. There are several opinions on the relationship between faith and science. Some people say science could only develop within the context of Christian faith, like Stanley Yaki, as you see here. He was the American who said that Jesus and his way of living and way of thinking and being honest and being real is kind of precondition for the real science that is about reality. And of course here also Moreland, he says Christianity is not against science, just the opposite. Christianity supports science. And then also Thomas Woods defends the view that the Catholic Church was a kind of eminent supporter of science, especially also in the 15th, 16th century. So what shall we say about that? I would like to talk to you in several parts, because otherwise it will be too long, on this relationship. I start with part 1, the case study of Galileo Galilei, Science and Church. We talk about the Aristotelian background of Galileo. We talk about his new science, and there are 3 subjects I would like to mention there. His use of experiments, the description in mathematical terminology, and also proofs, mathematical proofs in the philosophy of science, and as astronomy applied. So these experiments and mathematical descriptions were applied to astronomy, and that's a very interesting new way of looking at the world. In later programs, I will do the reactions, and we talk about the formal method as a solution of the demarcation of religion and science, but that's for a later date. And then I will look at some recent cases of the problematic relationship of science and faith, although I don't think there is any really problematic relationship. Okay, so we start with the Aristotelian background of Galileo Galilei. You know, Galileo lived from 1564 to 1642. You see here a young Galileo, a little younger and a little older one, a grey beard, a wise man, but he was quite emotional man too, but a very bright intellect, and he was really honest in his looking for the truth. So that's kind of real, scientist with all his heart, his whole mind. He was dedicated to discovery of the truth about nature. I would like to say something about Aristotelian background of him, because as a young kid he studied at the abbey of, I forgot the name of the abbey, but he had learned there about the demonstrations according to Aristotle. There is a book of Aristotle, Posterior Analytics, that describes the way of demonstrating things in science. Now, then Aristotle says all demonstrations should be founded on principles already known. These principles on which the science is founded must either themselves be demonstrable or be so-called first principles, which cannot be demonstrated, nor need to be, because they are evident in themselves. The principles, of course, are to be more certain than the conclusion. We cannot demonstrate things in a circular way, supporting the conclusion by the premises and the premises by the conclusion, nor can there be an infinite number of middle terms. So if this, then that, if this, then that, then that, then that, then that. There should always, kind of in demonstration, the first principles and the conclusion, they must be eternal truths. Otherwise you don't have a problem. Then or things that happen by chance, and that's a very interesting thing also when you apply it to for instance, Darwin, things that happen by chance, or contingency, or which can change, or of individual things, there is no demonstration. Very interesting, especially by this chance or contingency. That's a very interesting thing, because chance is not science. Some demonstrations prove only that the things are in a certain way rather than why they are so. And this is, of course, this why is the real demonstration. Now, the first figure of the syllogism is the best adapted. A is B, B is C, or A is C, that's a conclusion. If you combine these two, you get the real conclusion. The demonstration of affirmative proposition is preferable to the negative, and there cannot be both opinion and knowledge of the same thing at the same time. Now, these are just some principles of Aristotle, and later in his life, Galileo even wrote to Princess Christina that he remained all his life an Aristotelian in this sense, because there is nothing strange about it, and I think even modern scientists would agree to these principles of Aristotle. Now, so this second book of the Analytica Posteriora of Aristotle contains 4 scientific questions. That was what Galileo also learned in his beginning of his scientific career. Does the thing that you're looking for exist? What is the nature of this thing? The definition. What properties does this thing have? And then, especially, what is the causes of these properties? That's the real question. What are the causes? Science is just therefore not just knowing the facts, but the certain knowledge of the causes of things. Now, and I think every scientist would agree to that just knowing things, that's the beginning, is scratching the surface. But knowing the causes of the things, why things are like they are, that's the real thing. You can measure the mass of an electron, but why does it have this mass? Why is this mass so determined in this way and not in another way? So that's really science, and also in medicine, of course. You can see the outside of a body, you can see the skin color, but why? If you don't know why, the question why, then you don't know anything. Now, then there are, of course, 4 types of causes for Aristotle. That's a very interesting thing. We have the formal cause, which is the kind of determination, what are the characteristics. The material cause of what does it exist. The work cause, so how did it come about. And the goal directedness. That's a very interesting one, because Galileo skipped this one, because it's not measurable. But it is still very much present, and especially biology, for instance. We can see these 4 causes at work in building a house. That's the example of Aristotle. You have a formal cause, which is the outside, or even the design of the house, the form of the house, high, low, square, round, whatever. Material, that's of what kind of material the thing is made. The working cause is the workers that build the house, and the goal is to live in or to defend the city or whatever. So these 4 causes are for Aristotle, and for the young Galileo, the ordinary means of explanation, because causes is also explaining. Explanation is to look at the cause of things, and only when you know the causes you can explain things. Now, this Aristotelianism was very much present, especially in Padua, in this Giacomo Zabarella. Giacomo Zabarella, he was professor of logic and of epistemology at the University of Padua, and he combined this Aristotelian teaching of scientific method into his regress method. And as you see, it's already almost the modern way of dealing with proofs in science. You start with the facts. Sorry for the Dutch, but the facts seen as the effects of a cause. You start with, therefore, the phenomena. You see something and you think, oh, how is this possible? Then you have a hypothesis. So you see what is happening there. Hypothesis. And he called it metodo risolutivo. We would call it induction. We try to see many facts and then go to a kind of hypothetical cause. We call this process of combining all these effects into a kind of hypothetical cause, the negotiatio intellectus, and the mental look at causation. And then, if we have something in mind that might cause the phenomena, we try to prove the effects from this cause. And that's what he called the method compositivo, the deductive. And this is the proof. So this is the hypothesis. You talk about a certain thing and say, oh, what characteristics does this cause have in order to be able to prove the effects? And then you see whether that's indeed is. So if you look at an ill person, you see a certain color, you see fever, you see certain other characteristics. You might think of a germ or a virus or whatever. And then you can try to prove these effects from this virus. And this, of course, has to be the same and not kind of changing. Now, Galileo is known with this method through the Jesuits of the Collegio Romano. And then he also, of course, has these experiments. So Aristotle is okay. Aristotle is, however, not so much someone who experiments. Of course, he's a very good naturalist. He's very good at perceiving things in nature. On the other hand, he doesn't really do experiments. And that's an addition that Galileo, in his younger life even, added to his scientific methodology. As you see here, of course, Eureka. This Pythagoras, he said Eureka. He had to discern whether the crown was really gold, and he could see that the volume of the crown with the same weight was bigger than the gold. So the gold was less volume, the crown was more volume, and then you could see that the bath was streaming over because of the gold with more volume. In order to appear gold, therefore, you have to add certain things that are less heavy than gold. And if you have the same weight, then you know that there is less gold in it. And yeah, if you put then this crown into water, it will be make the water flow over because there's more volume in the crown. Okay, now another experiment which we are not really certain that happened, but it's a very nice thing, that is, of course, whether lighter and heavier objects fall faster or slower. So there you see that, there you go. You see a smaller ball, you see a bigger ball. The old idea is from Aristotle that the heavier ball will fall faster and the lighter ball will fall later. It will fall not so heavy. But Galileo discovered that they both fall at the same speed. That's because the attraction of the Earth is bigger when there is a heavier object that has to be accelerated. And it's smaller in a smaller object, but they will therefore arrive at the same time, which is a very interesting thing if we look at some experiments that we do on the moon, for instance.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Okay, so you see that there is this, I hope to get back to the tower, that he is correct with air, because of course bigger objects have more resistance from the air and they might fall even slower instead of faster than the smaller objects. Okay, then he had another very interesting perception, that is with the long wire that had this light in it, and he saw this light moving. And then he was thinking, if you have a heavier light, would then the speed of this kind of resonation will be shorter or longer, or is it only dependent on the length of the wire? And it turned out, with his experience, that it is only dependent on the length of the wire. And therefore, later, you can see Christian Huygens, the Dutch physicist, made a pendulum which makes use of this characteristics, that the time of the pendulum is only dependent on the length. And so they were able to have a seafaring clock that was able to also measure not only the breadth but also the longitude of the ships. He also did experiments with Bilancetta, with volumes and with kind of fluids. He wrote several books on that. De Motu, De Mechanica, Operazione della Compasso Geometrica. Also, it's all very much with experiments. For instance, like the bullets of a cannon. If you have 25 miles that you want to shoot, what angle do you have to shoot? For instance, that kind of thing. He also did all kinds of experiments with parabolic trajectories. So he had a table, and then he would fall. A kind of ball would fall, and then, depending on the speed and the length of the trajectory, the ball would fall further. And he discovered, therefore, the speeds of the falling objects, that the distance proportional to the square of time, which is a very interesting law. Then the third thing that he changed with regard to Aristotle is his mathematics, because he is very well known with the mathematics, and this is a very famous text from him. This is the greatest book of all, which is constantly open before our eyes. I'm in the universe, but one cannot understand it unless one first learns its language and understands the signs in which it is written. Now, it is written in the language of mathematics, and its signs are triangles, circles, and other geometric figures, without which means it is humanly impossible to understand its words. Without these signs, it is a useless wandering through a dark maze. Which is very famous, because in that sense, and the whole modern science is in fact based on this kind of expression, because any article in a scientific magazine is always full of mathematics. Without mathematics, it's hardly believable. So when you start talking in a mathematical language, people start believing it. It's very interesting. This, of course, he had from Eudoxus, which is a man before Christ. He had the elements of Euclides, of course. And the fourth one is Ptolemaios. Ptolemaios was a guy who lived in the old age, in the 3rd century before Christ, and he had to explain the strange movements of certain planets in the air. And he could only do it if this is the Earth. You see, the sun is turning around the Earth, according to them, but Mars is doing some strange things. He goes forth and back and forth again, and this only is explainable when you have a circular movement around the Earth with a little circle, epicycle they call it, that turns, and so sometimes when the speed is up, the circle, this added circle, will turn down, and then you have another movement, of course, than the circular movement. You can see it here. Mars, this is to the left, you see Mars moving, and then it turns back on its course, and then it goes further in this. Now, this is what you actually see in the heavens. Now, you can only explain that when you start doing the same thing. You see here the turning around of this epicircle, and then you see exactly what happens in the air. So that's what you do to explain the movement of Mars in the air. And that was the Ptolemaios solution to the strange movement of planets in the atmosphere. There were already astronomers busy with the astronomy before Galileo, of course. They have wonderful results. All kinds of, now for those who want to know it, you can see it. They already had a catalogue of 850 stars. The equinox points, the 21st of June and 21st of September. They determined the length of the sun year. Look at this, 365 years, the days, 5 hours, 55 minutes. It's only 6 minutes and 26 centuries too long, which is the before Christ that he could measure this. It's incredible. Now, yeah. Anyway, but then came, of course, the very genius person, Nicholas Copernicus. He was a Polish scientist, and he proposed that not the Earth would be in the center, but the Sun, because in that way it's much more easy to explain all these strange movements of planets in the sky. And so he put the Sun in the center, and then you have Mercury, you have Venus, Mars, Jupiter, Saturn, and then you have all kinds of things, and then the fixed stars. Of course, they didn't know about Saturnus, Neptunus, and Pluto. They didn't know anything about that, but it's already very, very good, of course. And so he said, one of the things that makes it believable that the planets are around the Sun, that they have, sometimes they're full, and sometimes they have half light. So if we look at with a telescope, of course he didn't have the telescope, but this is the unaided view. You just see this movement. But if you look at the telescope, that's exactly what happened with Galileo Galilei. Now, of course, the advantages of the hypothesis of Copernicus was that, of course, everything was much more easily explainable. Then, of course, there were some problems with that view, and then there was Tycho Brahe, a very, very famous observatory, best observatory in the dates on the planets. And he said, now let's take the Earth in the center, let's have the Sun turn around the Earth, but let all the planets turn around the Sun. So it's kind of medieval, it's kind of middle road. The Earth in the center, still Sun around the Earth, the planets around the Sun, which is a kind of nice solution to keep everyone quiet. But then came Kepler. He had all kinds of things, but it's very interesting. He wrote many letters to Galileo, but never answered them. But he discovered, before Galileo even pointed his telescope into the sky, that the planets' trajectories were ellipses, not circles. And then we have a person from Zeeland, Middelburg. He patented the telescope. A very interesting thing, 2 lenses, and then you see things far away. And what Galileo did was then produce his own telescope, and he discovered, for instance, mountains on the moon. This is his own drawings, where he pointed his telescope to the moon and said, hey, wow, this ought to be a very perfect planet, but it isn't. It's just as rough as the Earth, in fact. Then he saw the Jupiter moons for the first time, and he saw these moons moving around. So sometimes you have Jupiter here, 2 stars here, 1 star there, or planet then, or main moon, and there are the 3 moons together. He made very careful observations, and he saw the planets of the moons turning around Jupiter. He saw also the phases of Venus and the light, and this is only explainable when Venus is really turning around the Sun. And he wrote his Sidereus Nuncius, the Starry Messenger, in which he published all his results. Then 1613, he talked about the sunspots. He had a lot of perceptions of sunspots and all kinds of different things. So the Sun, not even the Sun, was a perfect object in the sky, which was a very discouraging perception, of course, because in old times the Sun and the stars and the moon were always regarded as perfect objects, but they turned out not to be. Now, let's have a little break now, because we're going to see the reactions to these discoveries by politicians, theologians, and the church, which is a very interesting period of the church history. Thank you for your attention.